Okay, so the this is a brief about myself. I did my graduation from IIT Roorkee. I mostly worked on large scale computing, and I worked at D Shaw in Mobi and Amazon. And my career mostly has been into data engineering, data science, machine learning, or pure computing, like building a web application. So I've done around 16 years of computing in the various fields. Why I say 16 years? Because I started quite early, as in I started working on the industry projects when I was in third year. Now, when I was even before I passed out from college, so I've worked on all kinds of computing work. So I'm software engineer by heart, but I enjoy explaining technologies. And that's one of the reasons why we started No Big Data earlier. And now we started CloudX Lab. So this is probably going to be the most interesting course, and this is probably going to be the most comprehensive and hands-on course available online as of today. And in the previous session, we talked about what is machine learning, and we also gave you demo of how does it look like when you play Mario. Okay, I think I'll just give you the demo this way. Okay, so basically in the previous session, what we talked about is we try to define machine learning, that it's a field of computing which gives the computers the ability to learn without explicitly program. Let me see if I can increase the volume a bit. All right, so let me. Okay, great. So we learned about what is machine learning, and it's a field of study that gives computers the ability to learn without explicitly being programmed. Then that time we talked about how computer learn to program itself, learn to play Mario by itself, and this is something which showed you last time. It's basically the example of reinforcement learning. And this is what we talked about last. So I'm going to skip ahead. Then we talked about the other use cases of machine learning which are out there and are being used. So probably the entire software industry is getting impacted with machine learning. So when I talk to my friends at Amazon or Google, they everywhere, the idea is that every engineer needs to learn machine learning in whatever possible way. Okay, so that's the scenario, and probably every product is going to get impacted. And when you learn machine learning, you not only learn to solve the given problem, you will also learn to figure out where all you can implement machine learning in your project, right? So I'll give you a quick example of how does many things change. So recently I was working with a company called Tribo, solving their problems on understanding emails, so that they could automatically parse email and create the booking. So they have the hotels, people send emails for the hotel booking. So they wanted to automatically figure out that this email is for the booking, and based on the email content, that this person would like to book a room in this particular hotel, and so on. So basically, when I was working with them and we were trying to solve the problem, so we realized that we could do many things with the similar eh, tools which are available as of now. So, so, and then the idea of creating the quizzes automatically came into play. So that became, so I published that as a blog post. Okay, so I'll show you. So the idea of auto quiz happened because we were working on machine learning. And so as you finish the course, you will be able to um, look at the bigger picture and look at how you can apply machine learning in your projects. Okay, so all right, so this is an important aspect of learning anything, that you'll be able to see things more clearly and would be able to apply newer tools in your existing work. Or you could, of course, this skill is definitely going to be required by almost every company, so it's going to be quite useful to everyone. So then after talking about the use cases of machine learning, we talked about that gathering data is an important part of the project or any process. And to get the data, we talked about IoT, we talked about distributed computing, then we talked about the spam filter, like if you had to build the spam filter, what will be the approach between traditional versus machine learning. Okay, so some of the traditional things we are going to talk about today, and as we move ahead, we will learn more and more techniques. Okay, so the traditional approach was that we will write the rules, while the automated machine learning approach is that computer program will infer the rules. So that's the difference between the automated versus machine learning. Sorry, manual versus machine learning. And then we talked about AI. What does it mean? So AI is basically a definition. Uh, it's the based on the objective that if if a computer can achieve any of these five sub-objectives, then a computer is artificially intelligent. Or a machine, if a machine can do these things, human-like things, then the machine is intelligent. That's what is artificial intelligence. And we talked about various other sub-objectives definition in detail. Then we talked about that machine learning is the machine learning is the core part of the artificial intelligence, and deep learning is one part of the machine learning. Okay, so we talked about this. This is something I would like to recap properly. All right, so okay, so is machine learning is about automatically inferring the rules instead of we writing the rules. But that doesn't mean that we do not have to write programs. We will have to write programs for machine learning. Okay, so machine learning has been categorized based on three criterias. Number one, the human supervision one. Second one is whether your program is learning incrementally or things are happening from the beginning, or how well the model generalize. Okay, so these are the three criterias on which we kind of categorize machine learning. So from the perspective of human supervision, the machine learning is classified into three categories. One is supervised, other is unsupervised, third one is reinforcement. Third one is reinforcement. Now, supervised means whether or not models are trained with human supervision. What does it mean? It means that we had certain amount of information available already against every record saying this is spam, this is not spam. That's kind of, we have supervision data. All right. So, okay. So Pawan had just joined. Should we have a quick intro with Pawan or should we continue?
Hey, this is Pawan.
Hi, Pawan. Yeah, a brief intro will be great. Yeah.
Hey, my name is Pavan, and I am here in George Washington, DC, working for Apple. I'm mainly working in big data on search engines like Elasticsearch and Spark and Hadoop. And I'm learning machine learning, so because this is the new technology. So
Won- Wonderful. Wonderful to have you in the session, Pawan. So you're working with Apple?
yeah.
Okay, wonderful. Wonderful. Great. Great to have you in the session. And okay. All right. Back to the supervised learning. So this is what we're talking about. So machine learning, if we look at the supervision, these are the three buckets. One is supervised, unsupervised, and third one is reinforcement. Supervised is where we have some amount of information. We have labeled information. Okay. The supervised is further classified as classification and regression. So classification is the training data we feed to the algorithms includes the desired solutions, okay? Which means that, let's say, we are talking about email. If some of the emails, we already know that these are the spams and these are not the spam, and we have this data very well labeled, then this problem is classification problem, right? And since in the classification it's about categorizing things, it's about putting labels on them, okay? And so basically in case of email filter, spam filter will be trained with many example emails called training data, and each email in the learning data contains the label if spam or ham. Okay, ham is basically what we call not spam. And models then learn to classify the new emails if they are spam or ham. All right, so the second kind of supervised learning is in which we want to in which we want to predict the value instead of a category or a label. Instead of saying is this a spam or a ham, is this a male or female, is this uh, is this A, B, or C? Instead of being an objective type question, if it's a subjective question whereby we have to predict a value, then we call it regression. We call it regression. The In regression, we basically predict the price of a car. Given a set of features called predictors such as mileage, age, brand, and we basically train the regression model, and we'll have to give a lot of cars example, including the predictors and the prices. Okay, so basically, let me go back to the example. Basically, given a lot of models and the information about the cars and their prices, if we are given an unknown car and we are asked about the price, this is a machine learning regression, supervised regression uh, problem. Okay, so this is what is. I'll go back to the diagram. So this is okay. So this is essentially the regression problem. Okay, so this is where we are. So supervised means that we have a data already labeled. Supervised could be where we have to predict a particular class, or maybe we have to classify an object into one of the categories. Regression means we have to predict a value. Okay, all right. So now let me ask you a quick question that that let's say there is a factory. The factory has many input parameters and we have to predict the produce, as in Given all the parameters, we have to predict how much produce is going to be this year. What will be the output or throughput of this factory? If we have to do that, will that be a regression or classification? That's right. So that will be regression. And great, great. And let me ask you more example of, given a lot of digits, okay, given the images of digits, if we have to put them into, we have to say whether it's 1, 2, 3, up to 9. We are given a lot of images already, and we have marked them 1 to 3, 0 to 9. And given an image, if we have to predict if that image is, if that image is 0, 1, 2, 3, up to 9, then is it regression or classification? That's right. So that's classification. Okay. All right. So that was classification. Now, what the way we do regression generally is that, what is regression? Regression is given lot of variables and we have to predict a price, right? So what we do is we draw, if we draw all of these data points on a graph and we start drawing lines through them, that's called linear regression. Okay, like here we are given data points and we are just trying to draw a line that fits the data points. Then that's called linear regression. In the regression, when we are trying to fit a curve or some kind of thing, we'll go into more details as we go ahead. I'm just scratching the surface. Okay.
Yeah.
Yes, Pavan, go ahead.
Sandeep, one question I have. In graduation time, in statistics, we learning something similar,
Hmm.
like a lot of regressions and sampling, where we do also some sort of prediction there. So is
Right.
that something same, or I mean, how the statistical learning different with
Yeah,
machine?
yeah.
Mm.
So basically, the statistical learning is something. Most of the part of the classical machine learning is statistical learning, and then there are a few more algorithms, and afterwards, the neural net is also part of machine learning. So the entire wherever we are predicting value, whether using the classic statistical methods or using the neural net or using the newer techniques, all of this is part of machine learning. Good question. Mm, all right, did I make sense to you?
Yeah.
Okay, great. All right, you can also use this chat box, so that'll be easy for you to quickly ask question. And all right, in case the question is bigger and you think that it's better to unmute, feel free to unmute. Okay, great. All right, so basically in the regression, okay, there's a good question. Question from Nouri: if the output is a value from a set of known value, it is classification. Otherwise, if we are trying to predict a value and guess the value, is called regression. Okay, so in the regression, what happens is we try to fit in, given all of the data points, we'll try to draw all possible lines, whatever fits, and then we will also talk about in the course about something called gradient descent. Now, trying all possible lines is not a great solution, right? There would be many lines, changing the slope, changing the position, and all of that. There could be many lines to fit into the data. So instead of trying all possible lines in case of linear regression, we go into the direction that's yielding the better results, right? And we observe that changing this variable is giving us better results, so changing that variable in this direction is giving us better result. This is called gradient descent. I'm trying to oversimplify it, we will go into more details about gradient descent. Gradient descent is a on the heart of it. It's basically an optimization in of drawing the lines. Let's say there is a whiteboard and you're trying to predict something by drawing a line that this is how my salary looks like. So instead of trying out all possible lines, what we do is we basically start somewhere, then start shifting the line, and then observe how well changing the slope is giving us results. If it's giving good results, we start going in that direction. If not, we start going in the opposite direction. That is gradient descent in very simple words. So gradient descent is basically, imagine that you are blindfolded on a mountainous terrain and you have to find the best lowest point, right? It's pretty simple for humans. Like you can, if let's say I'm blindfolded on a mountainous terrain, so what will I do to find the lowest point? I'll I'll basically step, you know, if my I'll put one step forward. If that step went down, right, that means I am towards the downside. This side, the forward side is lower than the backward side. So I'll start moving to the forward, and if my next step or sorry, my last step went up, what I'll do is I'll turn around and start moving. So that's how the gradient descent is. Okay, we'll go into more details about gradient descent at later point of time. Now, the second part of the machine learning was unsupervised. Unsupervised means you're given a training set and you're given the data. The data is not yet labeled, and we are told to figure out some good patterns in it, right? Such as trying to find an outlier in set of numbers. Okay, good question from Pawan before we move forward. So gradient descent is only for linear line fit? Not really. Gradient descent is for everything, because the same thing is true if let's say we are trying to fit a curve and we are changing some variables and observing that curve is fitting better if we change this variable. So we move in that direction fast if we start changing that particular thing. Okay, so gradient descent is interestingly valid for almost every kind of algorithm. Great question. Now moving ahead. So unsupervised learning is about classifying things into buckets. Okay, given a data, we are asked that find the outliers, or take the case of Gmail inbox. Gmail inbox has many things in it: social, promotion, and so on. So instead of looking at this way, let's say Google guys thought that let's just try to classify, let's just try to put the all of the emails in 4 random buckets. Let us create 4 random buckets of all the emails. We will give the names to these emails later. So basically, given billions of email, create 4 buckets, any 4 bucket, such that the data in one bucket, the emails in one bucket are all similar to each other, right? So that could have been that could have been one of the reasons of creating these labels that Gmail created. Probably they created these labels later. They gave the name later that, okay, so these turn out to be something called promotion, this bucket, and this turn out to be something called social. This turn out to be something called updates. So they basically took the entire inbox and said that let's just create buckets without any names, and we'll give the names later based on what comes out. So So that when we do not have predefined classified classification criteria, or let me give you a better example. We studied all of the species of human race. Okay, so let me show you a better example. I think I have a better example here. So, right. So let's say we have all of the species of human race, and or not human race, the all of the species on planet, and we would like to classify them into hierarchy, right? Classifying this is basically unsupervised learning, and it's called hierarchical unsupervised learning, or sometimes we also refer it clustering. Clustering, this is called as hierarchical clustering. So given all the cars, if you would like to plot a tree saying which two cars belong together, which are very similar to each other, that's called hierarchical clustering. So, so basically this, what Darwin did is something hierarchical clustering. Okay. So monkey, say chimp and human is very closer to each other, and monkeys are closer to chimp and human, while mouse and rat are similar, horse and dogs seem to be similar, and so on, right? So basically, the hierarchical clustering, in hierarchical clustering, we know the entities, we have all of the information about the cow, we have all of the information about monkey or the chimp, and we build a criteria of the distance and then apply such kind of algorithm to give us this kind of a structure. This is part of machine learning. Now, the same algorithm, so unsupervised learning is also used in anomaly detection. Okay, we basically cluster things into two buckets, and based on certain criteria, one bucket could be normal, other bucket could be anomaly. Now, third is reinforcement learning. What we learned as part of Mario is reinforcement. The agent is in an environment, and the agent observes, selects a policy, takes an action, then gets a reward or penalty. It learns from it, updates its policy, and then it goes back to the first step and then observe the environment and goes ahead. Okay, so basically reinforcement learning is something comparatively new in the domain. All right, now, so I think this is what we've talked about. So playing the game like DeepMind's AlphaGo, as in Google played, there was a game called Go, and in Go, two players have to play on a board, and they need to eat each other's coins, and so what Google did was Google built a bot which was playing against itself, and it learned really good moves, and once it learned the moves, it was able to defeat the world champion of Go, and that's what that algorithm is, what they call it, AlphaGo. So, so basically, the reinforcement learning is is used at many number of places wherever we would like to learn. We would like our program to learn from an environment. So that's reinforcement learning. Now, the other criteria of learning increment is based on how incrementally do we want to learn. So in batch learning, we train the data. We keep on evaluating it. Basically, we train the data on we train the algorithm on entire data set, and then evaluate the solution, okay, and launch. While basically, in case of batch learning, we operate on the whole batch, okay. Now, the the basically the system is incapable of incrementally learning, and Once the system is trained, it gets pushed to the production. And if the data changes, the system has to be trained on a newer data. And this is quite important. So as I was describing to you that at InMobi, we were dealing with, say, around 200 terabyte data, and it was becoming really hard to churn that 200 terabyte data every time. So, so basically the what we were doing was the batch learning. In batch learning, we had to consume the entire data again and again. So what we started doing was we wanted to incrementally train our model instead of again and again operating on the whole data. So what we started doing was we first started to keep the last cleaned data, and then we started to use newer algorithms in order to do better predictions on the uh, on the suggestions for the users. All right. So this is batch learning. So in case of online learning, what we have is the system learns incrementally as and when data arrives. Okay, system learns incrementally as and when data arrives. So whenever we train a machine learning algorithm, we basically feed we so this is the way we start. We train the machine learning algorithm on the holistic data as of now, and then we evaluate solution, then we launch. And when it goes into production, more and more data keeps coming, and it keeps on running, it keeps on learning by itself, right? So so this is how it looks like. This is how it looks like, and this is quite important when it comes to learning, because the data is going to grow, and if your machine learning algorithm needs the entire data again and again to train itself from the beginning, it's going to take more and more time. Okay, so that's why the online learning comes into play. A question from Noor is, can you please give an example of machine learning, batch learning? Example, what's the output of applying batch learning of the data? Will it be classification or regression? Good question, Noor. Good question. All right, let me take a step back. Right. So question is, question is, let's say we are talking about batch learning. So batch learning could be of any kinds. It could be regression, it could be classification, it could be clustering. Okay, so it could be anything, right? So and it could be basically be reinforcement also sometimes, but mostly reinforcement is generally online, but you will see that ahead. So batch learning is a criteria on machine learning. I'll show you. So batch learning is the classification of sorry, the this is the way we're looking at machine learning when we talk about whether to learn incrementally or not. Okay, so if our machine learning algorithm is processing humongous data in one shot, and then again when we want to update it, we have to feed the entire data from the beginning. We call it batch learning. Okay, it could be any of these algorithm. It could be classification, it could be regression, it could be clustering. All right, so this is the way we are defining the machine learning problem. It is based on this. Right. So the first part is categories of machine learning. This is all of these are categories of machine learning. This one, this categorization is based on whether supervision is not provided or not. Supervision is provided or not. Here, the categorization is based on whether we are learning incrementally or not. Okay. So, all right, data makes sense to you. And then The third criteria of the way we are dividing machine learning is how they are generalizing or not. All right. So batch learning is when we process the entire data again and again, and online learning is when we keep on updating existing algorithm with only the new data that has arrived, not the entire data. Okay. So online learning is hard. Online learning is the place where we require a lot of work. Not all algorithms can be moved to online learning. Okay. Online learning is great in kinds of, say, reinforcement learning examples, and because there we basically have to, most of the reinforcement learning has to be online learning. Okay, so we'll go into more details on the online learning. The next one is instance and model based learning. So we'll talk about this again. So one is we create a model, other we don't create a model. Okay, so most machine learning tasks are about making predictions. Having a good performance in training data is good, but the true goal is to perform well on new instances. So system needs to be able to generalize to examples which it has never seen before. So how well they generalize is either categorized as instance-based learning or model-based learning. Okay, so let's say we had trained our system based on other data points, and we got a new instance. We got a new instance which is not an existing one, which is a different one, right? So it'll basically, if your system is very well able to take care of new instances, right? If it's basically trying to figure out what is the closest one, if it's trying to figure out which one is the closest one, and then having the existing data point to it, it's giving the result there. That is instance-based learning. We'll go into more details of it. I think that will be better. All right. So what such instance-based learning algorithms do is based on the similarity measure to other points, it will start giving the results. Okay, it'll start giving the results. So the system learns examples by heart, and when it encounters a new instance, it tries to see it. Oh, this one looks like the one which I remembered, and hence it would be this. So that's instance-based learning. Okay. So spam filter flags emails that are identical to the known emails. Also the emails that are similar to known emails. This requires measures of similarity between two emails. Okay, and could be the number of common words. All right. So basically the instance-based learning, the way it works is, so as it receives a new instance, it will try to find a similar instance like the new one. And based on similarity, if it is really close to an existing known sample, it'll give the results. Otherwise, it'll fail. Okay. While model-based learning is we basically create a kind of model, like in this example of say classification, we have created a model that that this is a kind of line. Anything within this line is uh, uh, A, and outside this line is B. So we created this model. So now if we encounter an instance even at this, which is not very similar to all, you'll be able to say that this is triangle, this is square. So it builds a model which can generalize well. Okay. So based on how well your model is generalizing, we 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 define the two categories of learning: instance based or model based. Okay, so model based learnings are better and most stable, and the objective of most of the machine learning algorithms is to be able to generalize pretty well. Okay, this is this is something which we do when we have no other way to generalizing. Okay, this is the easier. Instance-based learning is something really simple and can be done quickly, while for model-based learning, it requires a bit of hard work. All right. So then we talked about neural network. We'll talk about this again as we go ahead. So people realize that that out of all the mathematical ways of predicting things, out of all the ways of predicting things, the one that works best is a neural net. Okay, a neural net. What is neural net? Neural net is neural net is basically many small mathematical units called neurons connected together, right? I'll so tell you what does it mean. So artificial neural net, or ANN, is a branch of machine learning in which we took the inspiration from biological neural networks that constitute the animal brains. Okay, so we learn progressively to improve performance to do tasks by considering examples, generally without task-specific programming, whether it's image or not. So basically, here, this looks like complicated. I think I'll describe it in a simple way. So if you think about neuron in the human brain or animal brain, the neuron is actually very simple thing. It is it is it it takes it takes the input signal and gives some output signal. So neuron is actually pretty dumb. Okay, neuron is actually pretty dumb. It takes some signal, it gives out some signal, right? On the same model, people wrote computer programs which, just like functions, the way we have functions, that it takes input and it gives out output. So they designed it in this way. The only difference is with the neuron is that it is plastic. What does it mean by plastic? Plasticity means the neuron will change itself in order to match the output. Each neuron will have a coefficient, just like when we are drawing lines, we had two things, slope and the c, the distance from the center. So just like that, just like while we were drawing lines, we were learning a coefficient. In the same way, neuron also learns some amount of information, right? So imagine this: if neuron is this knob, okay? This is a knob. On the left hand side you have hot water, on the right hand side you have cold water, and then you're feeling the water temperature. You don't have a clear demarcation of the exact temperature. So what you do is you turn on this, and if you'll start maybe from the middle. Okay, if it's okay, then you're good to go. If, let's say, it's really cold, you will turn the knob to the left and then check if it's going well. If not, you will turn to the right, and so on. And you don't even know that left is cold and right is hot. Let's say you are in a new hotel, and there you have to take a bath. So what you'll do is you will start somewhere from the middle, take a keep on turning this knob left and right, and keep on figuring out which 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 position of this knob is giving you the best results. Okay, is this example clear to all? So uh, uh, I I mean, here I'm trying to show you that there is a knob which is basically controlling the flow of the water from hot and cold. And what you do is you basically start somewhere in the middle, and you don't even know that left one is, if you turn it to the left, it'll give you the hot water. If you turn it to the right, it'll give you the cold water. So what you do is you try all possibilities, and as you try, you will become smarter and smarter, because you will know that the cold water was on the right hand side and hot water was on the left hand side. And you will also do fast things. If it came out as really hot, you'll just turn to the other side, right, really fast. and if it's really cold, then you'll turn to the other side fast. So that way, that's how you will, after a couple of trials, you will reach to a position where you will get the water that is tolerable for you, or water that's good temperature for you, right? So this is the job of a neuron. So what neuron does is, neuron's task is to match the end temperature given the input. So it'll try to change the it will try to change the knob, or we call it coefficient, and then it'll basically adjust itself to a particular position based on the circumstance, right? Now, if you have a complex problem, then people realize that if you basically create the entire chain of such neurons well connected, if you put so many knobs together, these are the knobs that are being capped. Okay, and these are basically software logic. It's a software program. Okay, and if we basically arrange all of these knobs in this manner in the layers, then people figured out that the results is far more better. So everyone, all of these knobs are maintaining their positions and those numbers which define their positions, and 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 basically given the inputs, maybe instead of hot temperature and cold temperature, there could be color, there could be how acidic or pH value is there of the input water, and and so on. There could be many other input criterias, right? And so basically, this is really a simple neural network which we have three layers. This is called hidden layer, this is output layer, this is input layer. So if the hidden layer, there are many layers, then we call it deep learning neural network. So deep learning is when you have multi layers of hidden network. Okay, so I'm trying to extremely simplify it. Okay, and uh, so the idea that I'm trying to drive is that neural network is nothing but a computer program. Neural network is nothing but a computer program, and basically we are just using a different algorithm to do the prediction. Okay, and this algorithm is based on a kind of a simulation of the neuron. Okay, and each neuron is nothing but a knob, and so multiple knobs, layers of knobs connected to another set of layers of knobs, and so on. That is the deep learning neural network. All right, so it's being used by, as of now, the machine learning and the deep learning is being used by many companies, almost everyone. All right, and here are a few examples, and here was one of the examples of showing you that how neural net was able to figure out the boundaries by itself. Okay, there are many deep learning frameworks: TensorFlow, Theanos, Keras, Caffe, and Torch, and the and the usual machine learning frameworks are scikit-learn, Pandas, and the for distributed we generally use Apache Spark MLlib. For simple ones we use this. Okay, coming back to it again. So since computation on TensorFlow is really CPU intensive, so it is very important to build a system which can work in parallel threads on parallel machines on multiple GPUs. GPU is graphical processing unit. We found that computation on graphical processing unit is really fast. So almost every deep learning framework uses the graphical processing unit, and although for learning deep learning, you don't really need a GPU. You can happily do the classification, or you happily do the deep learning using your normal machines. Okay, using CloudX Lab also. Though we have a deep learning machine, but we are yet to put it on the CloudX Lab. All right. So the simple frameworks. This is where we are starting. We are starting with scikit-learn, and we've already talked briefly about pandas. So we're starting with scikit-learn. We learn the basics of machine learning from the beginning, and then we'll go. Okay. A question from Tanmay. These are Windows based or Unix based or both. Most of these are can run on both. I'm not sure about TensorFlow, but most of these can run on Windows and Unix. Great. All right. So that was 1 hour of recap. All right. So I hope we all are on the same page. I hope you have not slept off. All right. Great. Great. So what we're going to do is we're going to do our end-to-end machine learning project. All right. So this is something. Yes, Noor. So what we have decided that we will work with a project from end to end, and then while working with the project, we will learn we will learn the concept then and there. We will digress as and when there is a need of any concept, and we will learn accordingly. The common fear in these cases is that what if we miss out on many uh, concepts, right? Don't worry, because the way we have created these projects is that by the end of these projects, you will learn entire thing. Okay, you will learn entire thing because that's how we have selected these projects. So we will not only, as part of this course, we will not only learn alone the deep learning. We will start with we will learn whatever is required. We will not learn something that's not required. Okay, so we're going to focus on what is required in the way by the way of solving problems. Okay, this is far more stable learning, because when you are on the project or you are have to solve a problem, theory wouldn't help. It would be probably this kind of examples that would help. Okay, all right. So it's an end-to-end machine learning project, and you will all have to do with us. Okay. So the objective is in the objective of this session is that we will walk you through the complete cycle of a machine learning project. And it's okay if you do not understand few code snippets. We will cover them in more details as we go forward in this course. Okay. So first of all, let's prepare the environment. You open Jupyter in the CloudX Labs MyLab tab. So if you are not there, you go to cloudxlab.com, click on MyLab. There you will see Jupyter on the right hand side. Click on that. You see Jupyter. Okay, is everybody able to log into Jupyter? It'll ask you for login password. You copy paste this one. Copy paste this one. All right, Kamal is able to do. Gizi is able to do. Bala, Bintao, Chandra, Giji, sorry, Noor, Pavan, Tanmay. Okay. All right. So are you able to open? Are you here and are you able to open Jupyter? So what error do you face, Abhinta? Do you want to show the screen? I'll stop sharing. Okay. So is it okay if I can take a look at your screen? You can share your screen. I have unshared.
Can you hear me?
Yeah, I can hear you.
Yeah, but I cannot see. Actually, I
Mhm.
show my share here.
Yeah.
Can you see my screen now?
Yeah. Could you share your screen, please?
Yeah. I open it. Cannot I share it? I did it, but I can
I
share.
think it would be showing you an extra dialog that there
Yeah,
you have to click again.
here. Can you see
Yeah.
it now?
Yeah, I can share
Yeah,
it now.
but lab detail. I don't know. I don't
Okay.
also
Okay.
it.
Okay. So yeah. Could you send a message in the chat? Uh, I'll quickly fix it for you.
Okay, sure.
So okay. Abhinav would be there. Abhinav, yeah. Can you? So it's Bintao Lee 6311.
Yeah.
Actually, what has happened is your account was created with the Hotmail ID. That's the reason. Thank you, Abhinav. Okay, so yeah, I think for now, what we can do is, okay, I think let's give the access to this account only. So, Vinta, you are going to use this account only, right?
Yeah.
Okay, let's give the access to this one, and we'll remove the other one. Great, wonderful. All right, we'll get it fixed soon.
Mhm.
Okay, no worries. We'll get it fixed soon. All right. Yeah, that's it. Anybody else is stuck? So once Abhinav gives you an access, you can click on refresh and you will be able to access it. I've muted you for time being. You can unmute yourself if there's a question. Okay. So he is probably creating your account and will.
Yes, I can do. Yes, I can log into now.
Okay. Are you able to click on Jupyter and log in there? Do you
Yeah.
see?
Yeah. It's starting. Start my server. Yes, I can log in now.
Wonderful, wonderful. Okay. Great. All right. If you may want to mute yourself now.
Mhm.
All right. Do you have anything else to say? All right. So anyway, so I have a okay. Good. All right. So I'm hoping that everybody is able to log into Jupyter and see this kind of screen. And once you're here, then okay. So these kind of delays are only in the beginning of sessions. And once everybody is up and running, things will be really smooth and faster for all of us. Okay, so we've installed everything for you so that you don't have to do anything of the installation. Okay, now the next thing is you have to log into here, say terminal here, right? And I'll just give you this command. Okay, so in the terminal, what you have to do is you have to say this command git clone and this. Okay, and press enter. Okay, since I have already cloned earlier, so all I have to do is git pull. It says that I have made some changes in the local one. So into this project, so what I'm going to do is I'm going to overwrite this. Okay, I'll say git checkout. Okay, so so basically, in case you also get stuck into this error will occur when you start modifying this. When you start modifying this particular notebook, then this error will occur that you have made some changes in the local machine. And in that case, I'm just saying git checkout so that it's reverting back. It's reverting back to the original. Okay. Okay. So after you log in into the CloudX Lab console, check out clone the repository which we have given. And since I had already done it, so all I had to do is git pull. All I had to do is git pull. Okay. And now I have this. I've checked out this. Okay. All right, that means you have the repository ready. Actually, this could be done from even the notebook. We could actually have done here itself, but right. But since we are cloning it using Git, so we can't really do that from here. Okay. Now coming back to the point. So we have once you have done that, let me go back here. I'll close this one which was already open so that we're all clear. And okay, so few things which I did was I logged into my lab, went to Jupyter. Jupyter opened like this. Then I clicked on new terminal. So terminal opened like this. And now here on the terminal, I did git clone. And since I had already done git clone, so all I did was git pull, git pull, and git pull I did after going into the ML folder. Okay, so when you say git clone, it is going to create a folder called ML in your home directory. This is your home directory. Okay, if you say, as you log in, you will log in into your home directory. This is my home directory. And here I said git clone. So once I did that, I went into ML folder. And inside here, I basically have all my work. Okay, so if you take a look at Python 1, you'll find all of the data sets. Okay, so basically this is the repository that we have pulled into our console, into our home directory. This is the repository that we have pulled. Okay, and it basically this is what we're going to talk about today. All right, so all right. So you should say, Giji, before saying git checkout, you should go to cdml and then do that. Okay, cdml. It would create a folder called ml in your home directory when you clone it. Okay, but that's not required for most of you. All right, that's not really required. So you clone the repository. That's it. Okay, so these are the let me say again. So log in into console, go to the console terminal. I'll say new terminal. Okay. In the terminal, you just say this. All right. You just type this command and press enter. So everybody has a copy of repository now. Balaji, Binta, Chandra, Giji, Noor, Pavan, Tanmay. Great, great, wonderful to have everybody set up. All right, so okay, now once you have cloned it successfully, you can go back to the let me just close this, leave it open here. Okay, now you can go back to Jupyter, the window in which contained this folder structure. There you would see something called ML. Do you see that? Click on that. Inside ML, you will see machine learning. And this is the project that we're going to work on. This is the one that we're going to work on. All right. So we are going to use a Jupyter Notebook containing all of our work. And all of the code is shared using the notebook so that you don't have to keep typing. And but you can keep on trying all possibilities if you have any questions on any piece of code. Okay. All right, everybody is able to open their project. Binta's question is, can I use my local Jupyter? It's up to you, but I would suggest that you use this one because here we have installed all tools that are required. Okay, so I would prefer that you use the this Jupyter. That'll be easier. Are you not able to use it? Do you want me to take a look at it, Binta? Okay, I'm stopping the share. I can take a look at your screen, and then that could also help other people. Yes, go ahead, please. If you are stuck, I can help you out right away.
Hi, can you see my screen?
Not yet, not yet.
Mhm.
I think it'll be giving you a dialog that you have to select in.
Mhm. Can you see my screen?
Not yet.
Mhm.
Yeah, now it is
Is this one?
showing. It is, yeah, I can see with your desktop. All right,
Mhm.
yes, you are able to open it. So good, good, good.
But I'm not familiar with the terminal, so I don't really follow that instruction in the terminal.
Okay, okay, show me.
Here, maybe I show you something like this. I'll follow to here. You can you see my screen?
Yeah, this correct. This is correct. You've done well.
Okay, so far I already work until this step for in the terminal.
Yeah, this is good. This is good. You don't need to follow other things. Here, basically, what we are saying is that if you already have done it long back, then you can pull the newer code using git pull command. That's all we were trying to explain.
Mhm.
Okay. All right. So looks good. Looks good. This is good. This is where we are going to spend most of our time. All
Mhm.
right. Yeah. All right. Wonderful. Wonderful. Great. So now all of us have the piece of code and we all of us have access to the repository. Great. In case you would like to modify this, feel free to clone the repository using GitHub. You go to GitHub, then there will be this repository, and then you can fork it. You can, if you fork it, you'll have your own copy. You can modify and commit in your way, and you'll have the entire control. Right? So, all right. So great. So we have done with the preparation of the environment. All right. So if you have not yet cloned, clone it. If already cloned, just update the repository, go into this uh, ML folder. CDML means go into the ML folder. Ampersand means there is another command. If this is successful, this piece of command will run. And basically, this is how we combine the Unix commands together. If you put the semicolon, the second command will run irrespective of first command ran or not. Ampersand means the second command will run only if the first one is successful. Here we are saying that git pull origin master only if cdml was successful. Okay. So all right, this is the machine learning the notebook that we're going to use for this project. All right, let's move on to the project. All right, so here is a checklist for machine learning projects, and I'm not very happy with the animation. It's really slow. Okay. All right. All right. So these are the 8 steps that we are going to follow in this machine learning project. These are kind of a checklist for machine learning projects. And though it looks like from the distance that machine learning is all about not having to code, but looks like there is a lot of work that goes into a machine learning project. So the first thing that we would like to do is, as part of machine learning project, you must do is frame the problem and look at the big picture. Then get the data, explore the data to gain insights, prepare the data for machine learning algorithms, explore many different models and shortlist the best ones. And once you have figured out the best model, then fine tune that model, present the solution, and then launch. Okay. So question from Tanmay is, this is prototyping in a small scale? No, actually this is a standard machine learning project. Okay. So we will learn the entire project by this way. Okay. So the way we are going is, I know that a lot of concept will be very new to you. So we will digress whenever we encounter a new project, new concept. Instead of first learn all possible concepts and then do some project, we're going to first do the project, and then this is walking backwards approach, and I prefer the walking backwards approach. Okay. So yeah, question from Tanmoy is a good question actually. Okay, so question is that, so Um, question is, is this for small scale or is this valid for big scale as well, big data as well? So this is kind of true for big data as well. So once So big data would come into as in um, we will have to in case of big data at this point we will realize that our data is bigger, so our one is the selection of model will change, and maybe the way we explore data will also change. Okay, so this is, you can say that the classic machine learning project, and not there's not much of a digression when we talk about big data, machine learning on big data. All right, so there won't be much of a difference from this approach. So we're going to go with the classic machine learning approach, and the same interestingly the same approach will be valid when you deal with, say, uh, on a large scale. So most of the work which I've done, even on the large scale, all of that follows this similar kind of methodology. Okay, all right. Though it sounds like common sense, but trust me, it would make your life easier if you just follow a kind of a checklist. Okay, great question. Now, the end-to-end machine learning project, the idea is to build a model of housing prices in California using the census data. Okay, so what we're trying to do is we are trying to build the housing prices in California. So this is how it looks like. So housing in California, we are trying to figure out the cost of it, the cost of a house. Okay, in a so in in various districts in California. So what we have in this uh, uh, plot here is, on one axis is longitude, on another we have latitude, and that's how the map is, right? This is how we draw the map. On one axis is longitude, other axis is latitude, and then we have various kinds of legends. The size of the circle shows the population, and the color shows the price of the house, right? Blue means really cheap, and red means really costly. Blue, or you can call it violet. So this data set is based on 1990 California census. Okay, so all right. So what we need to do is we need to predict the pricing of house. Okay, given other parameters, we need to predict the pricing of house. So first of all, let's have a look at the data. So first of all, we are going to import pandas, import OS. OS is required for the library, and then we are defining a function to load this. I'll just remove the animation from it. Okay. All right. So this is what we're going to do. And let me go back here. I think. All right. So this is what it is. So we are saying here import these packages. Then we are defining a variable defining the location in which we would like to save data, and then we're defining this function which will uh, read data from this folder. Okay, so we are not downloading it right now. We have put it in our GitHub so that you don't have to download it. So we are saying load data, as in we are going to read the CSV at this location. Okay, so this is where our data sets are located. Inside data sets, you have housing. Inside housing, you will see there is a housing.csv. Okay. All right. So it is trying to open in this. Okay. So here is some data. Okay. Let me just close it. It doesn't make too much of sense to do this. Now let's take a look at this data. This is where our data is located inside dataset, inside housing. So that's we are saying dataset housing. When we do not specify a slash in the beginning of path, it means it is relative to your home directory. Okay, so we are going to use this function. For right now, we are just defining this function. So we did shift enter, and now we are saying housing equals load housing data and take a look at the first 5 records using head. Okay, let me zoom out a bit. All right, hide the header. All right, so you see that there are 5 records 0, 1, 2, 3, 4, and this is the data look. This is how the data looks like. Okay, question from Chandrasekhar that what is the import OS looks like? Import OS is basically the import import OS is for uh, importing the module called OS, and the OS module is good for joining the data paths. Okay, joining the folders. All right, so we could actually do it also like this. All right, without having to combine it. Okay, so this is what it is doing. So if I say housing equals pandas dot read, okay, so this is what this code is doing. All right. Just a second. What does it say? Oh, can somebody help me? What mistake am I making here? I'm saying look, sorry. I think I got it. All right. So this is easier to. All right. So I think this is basically a simple way. We are saying pandas read CSV and we are providing this path. Okay. So that's it. So basically whatever we are doing here is basically this. All right. So you can see the data. Let's take a look at the data. A question from Tanmay, if the file is too large for the memory, what happens? Okay, that's right. That's where we are just taking a look at the head. And if the data is too large to fit into pandas, that's where we talk about Spark. Okay, we'll talk about Spark and other systems to do that. Good question. So yes. So the way we do most of these projects is, let's say, in this phase where we are exploring data, we generally take a small sample of the data, and then we observe it and understand it. Okay. In case the data is really huge, we just sample it and then apply the rest of it. This one is not lazy. This is basically loading this into housing, which is in the memory. Therefore, if the data is big, then it's going to overflow the memory. All right. And if that happens, what you need to do is you need to sample your data using one of the techniques, then or you just pick the smaller data and then use that. Okay. All right. To how to handle big data and all, we are doing that as part of our Spark course. All right, so take a look at this data. I hope everybody is able to see this data. Yes. Okay, so these are okay. So question is, what are these? These are row numbers assigned by pandas. Okay, these are the row numbers. Good question. Now, so we have longitude, latitude. We have this is the median age of the house. Okay, so what is this data? Here, each row represents one district. Okay, district that is located at this longitude, latitude, and there are rest of the attributes. You see how many. So basically for each district we are given one record, and here it is shown that in this district, if the median age of a house is 41, then uh, and rest of the parameters, then the the price of the house is this much. Okay, if the for the same district, sorry, for yeah, similarly for a same district here, you can see this district, it's it is showing if the total number of rooms in in that district is this much, and total bedrooms is this much, and so on. So basically all the parameters related to a particular district is what this row signifies. Okay. All right. Okay, so let's first frame the problem and look at the big picture. Okay, so dataset has following attributes for each block group in California: population, median income, median housing price, and more. Okay, so you can see that each row represents one district. There are 10 attributes: lo longitude, latitude, housing median age, and total rooms. Okay, and median housing value and ocean proximity. Okay, so all right. So if you look at the big picture, the block groups are the smallest geographical unit for which the US Census Bureau published the sample data. A block group typically has a population of 600 to 3,000 people. A block group typically has a population of 600 to 3,000 people, and we call them districts. Our model should learn from this data and be able to predict the median housing prices in any district. All right. Is it clear to everybody? Okay, I think we should take a break. So, so Tanmoy's question is, the price of house is the only dependent variable and rest are independent. That's correct. In this kind of problem, the one which we are doing, we are trying to predict the pricing or prices of house. Therefore, that's our dependent variable. Rest are independent. All right, that's our objective function. So let's take a break for 10 minutes and be back by 8:52 a.m. IST. You can post the time in your time zone. That could help others. Okay. All right, so should all right, so I'm back. Should we start now? Great, great. So, all right, so our model should learn from this data and be able to predict the median house price in any district. Okay, so given all the parameters, our model should be able to predict the median house price in any district. Okay, that's the okay. So what exactly is the business objective? So whenever the okay, I think I'll just keep it this way. This is far more easier than all right. So when we say frame the problem, basically the question is what exactly is the business objective? What is the end objective? And how does the company expect to use and benefit from this model? Okay. Above questions help us determining how to frame the problem, which algorithm to select, and performance measure to evaluate the model, and effort required to tweaking it. All right. So rather than just predict the data, rather than just predict something, you must know the end objective. You must know the end objective. And and basically the end objective could be really vague, really vague. And so in our case, the example in our example, this is where the model is going to sit. So this model that you are going to build, it's going to sit in the data pipeline. The data pipeline is nothing but many systems chained together, one doing one thing, other doing another thing. So it's going to sit here. It's going to be run by the system on the district data, and it's going to predict the district prices. So your model is going to predict the prices, and that could be used by other systems such as investment analysis or some other mechanisms. So that's what is the end objective. Let me just change these animations. Okay. All right. So sorry about that. I just okay. So model's output will be fed to another system. The system will determine whether it is worth investing in that area or not. Getting this critical right is very critical because it affects the revenue directly, right? So the other important thing that matter a lot and which we kind of always ignore. The other thing is, while framing the problem, you must ask this: what is the current solution? How it's being done currently? Okay. Is there any solution in place right now? And that will give you the clarity on the picture, right? So rather than just saying that current solution is completely rubbish and let's not even look at it, we should always look at the current solution. What's going on? Why do we think that the current solution is not good enough? Okay. Or why do we say that current solution is not efficient? We should know those parameters because that's what the problem definition is. It often gives a reference performance as well as insights on how to solve the problem, right? So we went around and asked like how do we currently predict the houses? How do we currently predict the housing prices? So we went around, asked the current team, and they told us that the prices are currently estimated manually by the experts in this domain. The team gathers up-to-date information about a district. Experts use complex rules to come up with an estimate, and this is costly and time-consuming. Estimates are not great. Typically, there's an error rate of around 15%. Okay, so what did we learn from the existing experts? They told us that the typical error is 15%. So if we can bring down that error to less than 15%, we're doing a good job, right? And estimates are not great. I mean, the other thing is we realized that it is costly and time consuming. That means if we are able to bring down the error rate to less than 15% and make it really fast to do that, it would be quite useful. Okay. Now, next thing that we ask is what type of problem, what type of machine learning problem it is. Is the problem supervised, unsupervised, or reinforcement? Who will help me right now? So what do you think? Is this a problem of supervised, unsupervised, or reinforcement? That's right. Is it a classification, regression, or something else further in supervised? That's correct. That's correct. Should we use batch learning or online learning techniques? We'll start with batch, and if required, we will put it on online. Okay. Batch should be good enough because we will train our model on existing data, and then we'll fit our model into the production, and where or we'll deploy our model to the production where it will be used by other systems or by other teams to predict the prices. Okay, so it's a supervised learning task. Data has labeled training examples, right? And each row in the data has expected output, which is the district's median price. Second is it's a regression task. You guessed it right. We have to predict the value. It's a multivariate regression. System will use multiple features to make a prediction. All right. Should we use batch learning or online learning techniques? Since there is no right now the continuous flow of data coming into the system, meaning we are not getting census data, we are not getting census data every day, right? Census data happens only once in some 5 years or once in 2 years or so in, in different countries. So there is no continuous flow of data coming into the system. Data is small enough to fit in the memory. That's another important criteria to keep in mind. It's a question I think asked by Tanmay. So data is small enough to fit in the memory, so we don't need a distributed system right now. Distributed means like Spark or Hadoop or some other mechanism. So plain batch learning should do just fine. All right. Now, the next thing is we are trying to frame the problem. We are trying to frame the problem that what is our criteria? What is our performance measure? How do we say that there is an error of 15%? So we come up with a performance measure. So performance measure is generally in terms of how much error are we producing in predicting the prices of houses, right? And the way we do it is by the way of root mean square error. Okay, let's say we want to predict the house value based on the house area in square feet. Okay, we will be using something called univariate linear regression. Regression is trying to predict a value. Linear regression is where we are drawing a straight line. Univariate means it only has a single variable. Okay, all right. If we were just trying to, if we will use univariate regression based on based on sorry, let me frame the point again. So let's assume for a time being that we are trying to predict the house value based on house area in square feet. So we will be using, in such case we would be using the univariate linear regression because there is only one variable called house area, right? Since there is only one feature called house area, therefore we will be using univariate regression. Now, now the question is, what does it mean by root mean square error? And why do we need to know this? So basically, root mean square error is something that we learn from statistics is a good measure of performance. So I would like to take a little digression into the statistical inference. Okay. So let me take a, I hope that's okay with everybody. So I'm going to take a little digression into the statistical inference. How many of you have already studied statistical inference? Okay. All right. All right. So I think it's important to brief you about the way we used to infer a lot of insights using the statistics. That's something where is a foundation to machine learning. Even if we are using the most advanced techniques, the statistical inference will keep on coming into play. And statistical inference is basically the basis for most of the data churning, right? So the first thing that we learn as part of statistical inference is that there are two kinds of variables, numerical and categorical, right? Categorical is like good, bad, India, US, UK. So that's the categorical variable, right? In which the value is part of a category. Numerical is a number, a decimal number, or decimal number or a normal number, integer number, that's numerical, right? So numerical could be continuous or discrete. In case of continuous, the value has both limits, upper and lower. So when we say continuous numerical variable, it means the variable is having the upper and lower limits. Okay. While discrete means the value could be anything. There is no upper and lower limit. Categorical could be regular or ordinal. Regular means any categories. Ordinal means there is a order. There is a order in the categories like high, low, medium, and so on. Right? Regular categorical is something that doesn't have an order, like India, US. That's a country. That's also a category. Okay. So in our case, all of these variables you see here, you see here, which ones are categorical and which ones are numerical? Yeah, quickly. In our data set, the one which we are talking about, which variables are categorical and which ones are numerical? That's right. That's right. So the ocean proximity is categorical, and while rest of the variables are numeric. That's right. Thank you, Prateek. Thank you, Bintao. Good, good. That's correct. Now let's take another data set. Now, what is this data set? This data set is the number of requests for your data by various governments. So various governments ask the data from Google about your information, and that data is something that basically that number of requests is what Google publishes to the world, that these are the number of requests being asked by various governments across the globe. Okay. And these are the requests which are, so here, let me describe the data again. Here, it's a different data set. A question from Kamal is, integers are discrete, floats are continuous? Not really, not really. I'll explain to that now. Okay. So if we look at this data, if we look at this data here, these are the countries who are requesting citizens data from Google. These many requests are being sent by each country. Okay. Percentage comply. This is percentage. How many of these requests are being complied by Google? Okay. And then there are other variables, right? And hemisphere is northern, southern, and HDI is high, very high, and so on, right? So question to you is, which one is discrete and which one is numerical? So this one is discrete because there is no upper limit or there is no lower limit, right? While percentage comply is always between 0 to 100, correct? So this one is continuous, this one is discrete. All right. And this one is, C is what kind of categorical variable it is? This one is, which one is normal and which one is ordinal between C and D? Yes. So C is normal or regular and D is ordinal. And between A and B, that's right. So the A is discrete and B is continuous. Why? Because B has a lower limit and upper limit. It can be between 0 to 100 because it is in the percentages. All right. Yes, that's right, Kamal. The term continuous is little confusing. Probably these examples would help you understand a little bit more. Okay, so ordinal means there is a order in this, right? Like high, low, good, better, best, something like that. That's there is all right. I hope this is clear to everyone. All right, ignore my last post. Okay, good, good. So yes, so I think it's clear to all of you. So discrete means any numerical value, decimal or integer. Continuous means something that has upper and lower limit. Okay, and the upper and lower limit. While the in the categorical means there is a basically the category of things, right? While in the categorical, there are two kinds of categorical variables. One is called regular and other is ordinal. Ordinal is the one that has some kind of order. While say if there is a color here, it is basically the regular. If there is something like high, low, medium, or good, better, best, or closer, closest, and far, and so on. So that's ordinal. All right. I hope it's clear so far, the variables. Okay. It's just a terminology. It's not too much of a science. Yes, Kamal. So the better term could have been bounded, but I think there is a reason why they call it continuous. All right. Now, very often we will be referring to probabilities and in our analysis. So I would like to brief you a bit about the brief you about the probabilities. Okay, I hope that's okay with you. That will probably refresh your memory a bit on the probabilities that we learned in school. Okay, so what is, first of all, what is a random process? A random process, we know in a random process we know what outcome could happen but do not know which particular outcome would happen, right? When we throw a dice, we know that either of 1 to 6 would happen, but we do not know which one exactly would be the outcome, right? Similarly, tossing a coin. While tossing a coin, we know either head or tail would come, but we do not know whether it would be head or tail, right? So, so chances or probability is something, chances or probability is something which is between 0 and 1. Okay, it's a decimal number between 0 and 1. If probability of something, a coin, if probability of, say, let's say there is a dice which has sixes all over six faces, right? So probability of getting a 6 is actually 1, right? Similarly, a coin with having head on both sides, the probability of head coming out is 1, while probability of tail is 0. Is it clear? Probability is the chances of something, the in terms of but you can say percentages, or you can say in terms of a number between 0 to 1. Zero point 0.5 means it's 50-50, 1 means it's 100%, and 0 means it's no chance at all. Okay, that's how we define probability. Probability of A is between 0 and 1. Now, here's a challenge to all of you. Question to all of you is, in a village, there has been a tradition that people would keep on having children until they get a boy, right? So the tradition is that if you get a girl, you are bound to have a boy. If the another one again is a girl, then you'll have to have a boy. And the moment you get a boy, you stop. Okay. Now, question is, in this village, what will be the ratio of male to female? Quickly. This is the tradition going on in this village for like 1,000 years. And question is, what would be the ratio as of today? Kamal says 50-50. Bintao says actually 1-1. Yes. Okay. Good. So any other answers do you think? Is it right? Will the total number of girls and boys, or total numbers of males and females, will be equal in this village? Why do you think so, Noor? Okay, let me rephrase the question. Tradition is that if somebody has a boy, they will not have any more kids. Why, if they get a girl, they will try again, and so on. Okay. Any other suggestions? But why do you think it is going to be 1:1? Why do you think the male and females will be equal in number in the village? Okay. Any other suggestions? Okay. So the ratio will be equal, right? Because it is we are not uh, impacting the outcome at all, right? Why? Because imagine that imagine that we were had we been, say, discarding I mean, or let's say we were trying to predict the kid. I mean, when the kids are in the womb, then we are trying to predict them, and then trying to, you know what do you call, do abortion or something. Then it could have been the other scenario. But here, if you see that naturally the ratio is 1:1, right? Since it's a natural process and we are not impacting that process, the ratio is going to be 1:1 no matter what. Okay, so probability is going to be 50-50, right? 0.5. So this is an important part, and a lot of why I've taken this example is because we always think of it as a conditional probability scenario, but it is not. It is not. Okay, it is not. So whether you have thrown a dice 3 times before or thrown a dice 10 times before, the chance of next one is going to, next one is going to be the chance of 1 or chance of 3 is going to be the same. The dice is not going to get biased because you have thrown the dice multiple times already. Okay, so similarly for a coin, no matter whether we have thrown the coin thrice or twice or 4 times or 10 times, the next outcome is going to be either head or tail with equal probabilities. Okay, so it's going to be the probability of getting a head or tail is going to be equal, and hence for everybody the probability of child, the newborn, going to be equal. Probability of having male or female kid is going to be equal, irrespective of how many kids they had or what they have in mind. Okay, it's going to be equal. Do I make sense now? So so the answer is 1:1. All right, let me ask you a further question. What is the probability that the sum of the pair of the fair dice when rolled is 4? Okay, what are the chances that we'll get a total of 4? Okay, thank you, Kamal. That's probably a better way to ask it. His way of question is that if, let's say, somebody has 10 girl children, what is the probability of 11th child being a boy? The chance of 11th child being a boy is going to be equal irrespective of how many girl child they have. Good, good, good. All right. Now let's come back to this question where we have 2 dice and we are going to throw them, and we want to get 4. So we want to get 4 as a total of both. And how we can get 4? We can get 4 by when we get 1 on one and 3 on another, 2 on one, 2 on another, 3 on one on another. So these are 3 possibilities, correct? So question is, what is the probability that the sum of the pair of a dice is 4? We can only throw the pair at once, and we want to find the probability. What are the chances of getting the total as 4? Okay, here let me ask you question further. What are the total possible ways in which a pair can be rolled? As in, what are the total possible numbers that could appear? We are throwing 2 dice, right? So first die could vary from 1 to 6. Second could vary from 1 to 6, right? So it would be 6 into 6. That's right. So the total possible ways will be 6 into 6. So if we had, can I just draw and explain? I think this is important because it's going to be used again and again, and I want to further take it. So if we have 2 dice here, all right, and so let's say we are throwing this die. What are the possible outcomes on on the first one? It's going to be 6, right? And the second one could be 6, from 1 to 6. It could be 1 or could be 2 or so on. So the total outcome could be 1 here, 1 here, 1 here, 2 here, 1 here, 3 here, and 1 here, 4 here, and 1 here, 5 here, which means that for every dice there could be total 6. Every number on first dice there could be total 6, and hence it is 6 into 6, right? 36. The numbers that could appear total numbers that could appear is 6 into 6, right? And instances when the sum is, what are the chances, what are the scenarios, when the total could be 4? What are the scenarios where total could be 4? This could be 1, this could be 3, right? This could be 3, this could be 1, and this could be 2, this could be 2. Correct? Is there any other possibility of getting total of 4? So we got, say, 1 here, 3 here, okay? Or there could be, right? There could be a scenario where 2 and 2, right? And so on. So these are the 3 possibilities. Yeah, we are throwing 2 dice, so we are saying all possible ways we could get 4. Okay? And hence the probability is 3. There are 3 cases. The total number of 36 cases, right? And in 3 cases, we are getting 4. So our probability of getting total of 4 is 1 by 12, right? So 3 by 36 or 1 by 12. Do I make sense to you? So if we roll these dice 36 times, there are chances that we will get the total as 4 3 times. Is everybody with me? Balaji, Pintao, Chandra, Gigi, Kamal, Noor, Pavan, Pratik, Shahrukh, Tanmay. All right. Okay. So a random variable is a variable whose value is unknown, or a function that assigns value to each of an experiment's outcome. Can be of multiple types. Depending on the type of the quality measured, it could be continuous, discrete, or categorical. Sorry, depending upon what is it that we are measuring, okay, it could be continuous, discrete, or categorical. Okay, a question from Noor. So this means that if we throw both dice together 12 times, then probability is that we will get a sum at least 1 times. Yes, if it is the probability, it doesn't mean that it would come, but yes, the chances of it coming is really high. Okay, now this is an interesting fact. So the way we did for 4, right? The way we tried to get 4. If we do that for all of the number, say for 2, okay, what is the chance of getting a 2 is only in the case where both the dice will get 1, right? 1 and 1. So the probability is low. For getting 3, it could be either 1 and 2 or 2 and 1, right? And the probability of getting 4 is the situation is 1 and 3, 2 and 2, and 3 and 1, right? And similar is the case with 5. Now, if we draw the probabilities of all of the numbers that we are expecting from minimum to maximum, the curve looks like this, like a bell, like a bell. Okay. If we keep throwing the dice this way, the 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 outcome would look like this. Okay. On y-axis, we are drawing the probability. Okay. On the x-axis, we are drawing the total. So in a random experiment or a survey or a procedure of statistical inference, the distribution generally comes out to be this way. Okay, like in a class, there will be many people on the marks, like in the middle way. There will be very few people who have really low marks and very few people who have really high marks. Okay, so on the y-axis, we have probability or total numbers, and on x-axis, we have a parameter. All right. So that's called probability distribution. Okay. So probability distribution assigns a probability to each of the possible outcomes of a random experiment, survey, or a procedure of an inference. Okay. So the probability distribution is nothing but how is the probability of every outcome distributed. And generally, this distribution looks like a normal curve, looks like a bell-shaped curve. Okay. All right. So when we draw graphs or charts in these cases, like the probability distribution, okay, the graphs could look either left skewed like this. Left skewed means there's a lot of values to the left. Okay. Right skewed means there are a lot of values to the right. Okay. Symmetric means there are both sides from equal values from the peak. Okay. These are called skewness. Skewness is basically on which side of the peak are the maximum number of values. So, right. The other characteristic. So we talked briefly about plotting a graph, right? Probability distribution. So when we draw such kind of graphs, here this is basically a graph which we have shown. The probability of each of the dice, probability of getting each of the numbers from 2 to 12. All right. So the okay, the other criteria, the other terminology that we would use is modality. Modality is if we are drawing a graph or a chart, if there's only one peak, then we call it unimodal. There are two peaks, we call it bimodal. Uniform is like there's no peak as such. Multimodal is when there are more than bimodal. Okay, the way we'll do is we will plot the histogram or plot the probability distribution. Please note that histogram and probability distribution are very similar thing. What's a histogram? Histogram is plotting the frequency of every sample. Okay, every outcome. If we draw draw the frequency, as in how many times 2 occurred, how many times 3 occurred, how many times 4 occurred, how many times 5 occurred, how many times 6 occurred, and so on. Or what's the probability of each of these? The graph is going to be similar. So probability distribution looks like this. So this is okay. So when we draw such kind of histogram, it could be left skewed, right skewed, or symmetric, and it could be unimodal, bimodal, and uniform or multimodal, right? The way to compute is do this is you draw the histogram, you draw these rectangles, okay, and then you drop a big noodle on top of this, and based on that you can always look at it and say that this is unimodal and this is uniform. Okay, you take a big noodle and drop on top of the chart. Okay, and why does modality matter? Okay, why does modality matter? Let's say there is a school, there is a school, and there's a school, and you basically draw the histogram of teachers and kids. On the histogram, on y-axis it's the total number, and on x-axis here we have the heights. Okay, here we have the heights, and so here we have the heights on x-axis. On y-axis is the total number of people on that height. It is showing that there are these many people between -2 to this, and there are these many people from this to this, then there are, and so on. And similarly, there are some uh, uh, other people where we have the heights from 6 to 10. So what do we, the moment we plot this kind of a histogram or a chart and we see that there are bimodal, then we will realize that, okay, there is something wrong here. There is basically two groups of people. One is kids and other is teachers. So this is where the modality gives us quick uh, insight into our data set. It gives us kind of brief overview of what does our data set look like, right? Now take a look at this one. Take a look at this one. It, the histogram here doesn't have this peak. It's basically there is no modality. It's uniform. This one is uniform, and you know why? Because 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 this one is the last digit of SSN. So last digit of SSN number could be anything. The probability of last digit is same. So whether it's 0, 9, 8, or any other number, the probability is same. So whether it's 9, 8, 6, 5, 4, the probability is going to be more or less same. That's why the graph looks kind of a flat. The graph looks kind of flat. So the total, let's say if you have 1 million SSN numbers and you pick the last digit of all of this, do a frequency computation on the last digit, as in how many times did 0 occurred, how many times 1 occurred, how many times 2 occurred, and so on. You'll find that the graph is flat. Okay, the graph is flat. All right. So when you look at the data sample, one of the things you should generally do is do the frequency analysis. If it is natural process, the chance of it being normal is really high, meaning having this kind of a peak is most of the natural process data is going to be this. Okay. If let's say you asked your friend to give you a data on something, and when you plotted the data of that, it comes out to be flat. Okay, and from that you can say that the data is fake. Okay, you can confident in many times when you know for sure that the data was supposed to be such that on the middle side there will be more people, on the edge cases there will be less people, but if all of them are equal, then the chance of it being fake is really high. Okay, the chance of it being, so if you, let's say you ask somebody that, can you give us the marks of the class, can you give us the marks of the class, and when you draw the marks of the class, you found that the data was kind of like this, okay, not like this, then that means the data is fudged, because in reality the marks of the people in a class follow a normal curve like this. This is where the modality comes into play when we talk about prediction. All right. The other quick way of looking at the data and trying to understand the data is by the way of something called box plot. What is box plot? Box plot is very similar to box plot in philosophy is very similar to the normal curve. Normal curve as in the histogram, but in a different way. Here we basically draw a box. We basically draw a box. This box contains, the box contains the middle 50% of the user. The box is drawn such that the left edge is drawn at the point where the 25% of the population is to the left of this box. 25% people are right to the box and middle 50 is in the box. Okay, imagine the case of life expectancy. Life expectancy, when we draw the life expectancy of a country, you will find this kind of chart. So here what you see is total number of people who lived up to 65 are these many. Total number of people who lived up to 65 are these many, as in to the left. Okay, and this is 77, and this is the middle range. Okay, so this is how you generally plot the graph. Here, this is the median. Okay, and so on. So this is called IQR, or interquartile range. Okay, so range of middle 25% of the data is drawn as a box, and distance between the first quartile and this is basically the distance between the first quartile, which is first 25%, and third 25%. Okay. Okay. All right. So left skewness means there are too many numbers on the left hand side of the peak. And when you draw box plot, normal curve, and the histogram, this is how it looks like. Okay, this is how it looks like. Okay, I hope this diagram is clear to everybody. So the way we draw, again, let me, because I know that box plot is a little confusing for most of us. Again, so first of all, we find out these edges. Okay, we find out that what is that edge, what is that age or life expectancy, okay, below which there is 25% population. If there are 100 people and we ordered the data such that that there are that the data is ordered by the life expectancy. So what we do is we will start counting from the one side and say that, okay, we've reached here, till here we've reached 25% people. Okay, so this is where the 65 is. So we draw a line, we keep moving, and or we can also move from the right hand side. We keep counting the total number of records. Okay, and the moment we hit 25% record, we say that this is the second boundary of our box, and hence this is how we're going to draw the data. All right. So we start from the left hand side. The moment we hit the 25% records, we call it the left boundary. If we start from the right hand side and hit 25% records, we draw it as second boundary, and that's how we draw the box. Okay, so this is called a box plot. Okay, so box plot generally gives us an idea quickly that how does our population look like? How does our data, most of our data, like 50% of the data is how, whether it's to the left, to the right, and so on. Okay, if there are too many numbers on the left hand side, okay, all right, I think this is clear to all of us. Now moving ahead, the line in the middle is the median. All right, now the other thing that we often struggle with, is the central tendency, and central tendencies are really hard to define. Okay, imagine, let me ask you a very simple question. Imagine you're given two, let me pick up a better color. Okay, let me ask you that, let's say there are this group of dots, and there are these group of dots here, right? You see there are two groups of dot, one is on this side, other on this side, right? Now if I ask you what is the distance between these two groups, how would you find the distance between these two groups? Okay, that means that you need kind of a center point to define a population. You need a middle of it. You need something that you need to mark a center. Thank you, Bintao. Yes, so you need to be able to mark a center here. Now, how do you mark a center? That has been the really hard problem to solve. How do you mark the center from here to here? Okay, what could be the possibilities of marking the center? Yeah, how would you, what are the ways of marking a center? That's a question for you. Given a data, how would you find the center of it? Okay, Vidya is suggesting the weighted center, good. And average, it could be median, it could be weighted mean. Good, good. Wonderful. So yes, these are the three measures of central tendency. We also call it point estimate because a point is representing a whole population. So that's also called a point estimate. Okay, so mean, median, mode, as in mean is arithmetic average. How do you compute arithmetic average? We sum up the all of the numbers, we divide by the total numbers, right? The median is the midpoint of the distribution. Okay, we call it, sometimes we call it 50th percentile. Okay, how do we define that? We basically order the records and we go to the middle half of the numbers, and that is the median. All right, so, and the mode is most frequent observation. Now so let me show you this. Question is, this is how we are generally computing. Let's say we are given these numbers. You see these numbers, 75, 69, 88, 93, 95, and so on. So the average is going to be, mean or average is the same thing. We sum up all the numbers, divide by the count, and that is the mean. Mod is Mod is basically the most frequent observation, as in we do the frequency computation of this data, and find out which one is the most frequent. That's mode. Median is you order this data from increasing to decreasing or decreasing to increasing, and then pick the middle one, right? If these are odd numbers, it's easy to pick the middle one. But if these are even numbers, what you do is you sum up the middle two and divide by 2. Okay. If these are even numbers, then we pick the middle two and divide the sum of the two, compute the average of the two. Okay. Question from Tanmay is, if it is distinct, what is the mod? Good question. We can't compute the mod in that case. Okay. So mod becomes irrelevant if there is the frequency of each one is 1. Question from Noor. And if more than one number has same frequency, then what is the mod? Good question again. So that's exactly the reason why we do not like the mod, because in that case it's difficult to compute the mod. In that case, either you pick one, or then you either compute the average or mean. Okay, that's the problem with the mod. Okay, so generally whenever in the mod also, if there are multiple numbers at the same, we basically do compute the mean of those numbers. Okay, mean, or we call it average. All right, so question to you is, what would be your favorite way of choosing the central tendency or point estimate, which defines the center, mean, median, or mod? What will be? Pawan says median, Kamal says median. Why not average? Okay, go ahead. So Kamal says that actually it depends on what we are measuring. So Noor is suggesting that if it is continuous data, then average. And for discrete data, we use median. Okay, okay, good. Yes, very good point, Kamal. Thank you. So yes, so median is mostly preferred in case of data analysis or machine learning. We prefer median. Why? Because median is not affected by extremes. Let's take a case that, let's say we had numbers like 1 to 6, right? The mean of 1 to 6 is 3.5 and median is 3.5. Now suddenly we replace 6 with an extremely big number, or the observation number 6 is gone really haywire, right? So mean will suddenly jump from 3.5 to 169, while median remain the same. Do you notice that? So if one of the numbers is kind of outlier, or kind of gone beyond what we have done, uh, what our usual numbers are, then the whole center goes haywire. It just went out of the whole population, right? if 4 is replaced by 400, still the median will slightly shift. Good point, Tanmay. Median will not shift, will become like, how much will it become? 150, right? Not 150. Then it'll become 3 point, no, it'll become 4. If let's say 4 is replaced by 400, right? The numbers will become 1, 2, 3, 5, 400, and 1000. Then the median will be between 3 and 5. That means it's going to be 4. The median will be, in your case, the example suggests by Tanmay, the example there, the mean will again jump further while the median will almost remain the same. Okay, so median is a better representative of the population. So the center is generally measured by median or mean, while median is robust because it's not being impacted by the extreme observation, 1 or 2 extreme rare observations, while mean is not so robust. All right. Similarly, the other thing that we would like to the other two, like the other criteria that we generally look at is spread. Spread is basically the how your numbers are spread on the number line, right? So we generally use IQR or the box plot to take a look at our spread, the spread of numbers, like where are our most of the 50% numbers and so on. So the robust way of measuring the spread of your numbers is using IQR or box plot. Okay, while standard deviation that we will study further, standard deviation is badly impacted because of few extreme observation, just like mean, because standard deviation is very similar to mean. Okay, and so on. All right, and so on. So central tendencies are used to represent the behavior of a population. In our example, since every record is about a district, every observation is per district, the most of the observations are listed in terms of median, like median house prices, right? Similarly, let's say if we are listing down the income per person or life expectancy per person, again we'll be using either the median or average, mostly the median. Okay, so this is where the central tendencies are used. Okay, and when we draw them on the graph, this is how they look like. So you can see that the median is more closer to the peak, while mean is towards the tail side. Okay, in all the graphs. So the when we talk about central tendencies or the point estimate that represent the center, we realize that the median is a closer representative of the numbers. Okay, the median is a better representative of the center. Okay, all right. So basically we have already talked about these. Now the measures of spread. Okay, so there are just, I think this is probably the last one in the statistical inference. So we can continue from measures of spread in the evening, in tomorrow. Okay, we will continue from here tomorrow at the same time. All right. So then we will continue to understand this data set, and we'll try to first explore this data and then try to predict the value of the median house price. Okay, given a house. All right. I hope this is not too boring for you. All right. So thank you, everyone. This is pretty much for today. We will continue from here in the next session. Thank you, Balaji. Thank you, Bintao. Thank you, Chandra. Thank you, Kamal. Thank you, Noor. Thank you, Pavan. Thank you, Prateek. Thank you, Shahrukh. Thank you, Tanmay. I look forward to see you tomorrow at the same time.